Hello everyone and welcome back to the C++ 3D game tutorial series. In this fourth episode, we will see how to create the device context, which will allow us to issue rendering commands to the GPU, enabling us to start rendering and fill the window content with a red color. As always, we will face three main parts: the requirements, design, and implementation of all the software components needed to create and use the device context. Let's start with the requirements. We need a C++ IDE. In this series, we use Visual Studio 2022 Community. The target platform is Windows. The target graphics API is DirectX 11. And last but not least, a good understanding of the C++ programming language is recommended. Now we can start the design part. In the previous episode, we learned how to create the swap chain class. This time, we will focus on implementing the device context. In Direct3D 11, the device context is the interface used to issue rendering commands to the GPU. Today, we want to create and use the device context to issue a command to the GPU that clears and fills our back buffer with a specific color. Once our back buffer is ready, we can swap it with the front buffer using the swap chain, allowing us to display the final result on the screen. Before to proceed, let's break down how a device context works. There are two types of device context in Direct3D 11: the immediate context, that is the default context provided when the main D3D 11 device is created. It issues rendering commands directly and immediately to the GPU for the execution. The deferred context, on the other hand, allows commands to be recorded into a command list without affecting the GPU immediately. This recorded command list can later be submitted by means of the immediate context for execution on the GPU. This decoupling between recording commands and executing them on the GPU allows applications to prepare rendering work in parallel, potentially improving performance on multi-core systems. However, it is important to note that the actual execution of those commands still goes through the immediate context. Let's see how to introduce the device context in our architecture. First of all, we will rename the render system to graphics device. A wrapper for a graphics API like the one we are building should be called graphics device rather than render system because it directly represents the interface to the GPU for creating and managing graphics resources. The name render system might suggest a higher level or engine-wide system that could include other high-level features, not just low-level GPU interaction. That said, since the graphics device is the software component responsible for managing the graphics API and handling its resources, we will also give it the role of creating the device context. Just like we have already done with the swap chain, we will add a simple create device context method to create our device context resource. In particular, the device context class will be a wrapper class around the deferred device context, the one used to record commands into a command list. The graphics device class will be responsible for extracting command lists from the deferred device context. Once extracted, the command list will be sent to the GPU by the immediate device context. We will also manage the rendering process in the graphics engine class by adding a render method. Let's break down the rendering process. First, we will use a deferred context through our device context class to record the rendering commands. Using this context, we will record a command that clears and fills the back buffer with color by passing a reference to a swap chain. To start, we will fill our back buffer with a red color. Next, we will pass the context to the execute command list method of the graphics device class, allowing the GPU to execute the recorded command. Once that's done, the back buffer should be ready and completely filled with a red color. At that point, we will call the present method of the swap chain to swap the back buffer with the front buffer, so the final image can be displayed on the screen. If you have any questions, doubts, or comments about this topic, feel free to leave them in the comment section of this video or on our Discord server. You can find the link to the Discord server in the video description. Also, if you find these tutorials helpful, please consider supporting their development on Patreon. Every contribution makes the difference, no matter the amount. Great, we have gathered all the necessary information to start the implementation. Let's start by moving the graphics engine header file from the include folder to the source folder, since we are not planning to expose the graphics engine to the users of our DX3D engine. With that completed, we should rename the render system to something more appropriate. Render system typically refers to a high-level system that deals with game objects, components, and so on. In our case, we are actually wrapping the graphics API to handle GPU resources and dispatch through calls. A more suitable name would be graphics device. This also aligns with the convention used in Direct3D 11, which has a D3D11 device. Also, since we are managing the D3D device directly, this name fits better. At this point, let's rename the render system header file to graphics device, and do the same for the C++ file. Now, we need to replace all the references to render system with graphics device. To do this, we can go to Edit, Find and Replace, Quick Replace. A small window should appear in the top right corner of the editor. In the top text box, let's enter the name we want to replace, in this case, Render System. In the bottom text box, we should type the new name, that is Graphics Device. Next, click the drop-down control at the bottom of the window and select Entire Solution. We want to update this name across all files in the solution. Finally, click the small button on the right. A tooltip should appear showing Replace All. By clicking this, all occurrences of render system will be replaced with graphics device. At this point, we might see a warning message box saying that some files cannot be modified. Now, all render system occurrences should be replaced. Let's do the same thing for 4 other occurrences, variable names of type graphics device used throughout the codebase. To do this, copy and paste graphics device from the bottom text box to the top text box and update the variable names shown on the screen. If everything is replaced correctly, we should be able to compile our program successfully. If you run into any issues, you can find the code written in this episode on GitHub. Check the video description for more information. Next, let's take care of the graphics log utis header file. Here, we should rename the macro the X3D graphics log error and throw to something more meaningful. Let's use the X3D graphics log throw on fail. This makes its purpose much clearer. Let's now debug our program to ensure everything is working correctly. Last but not least, let's go to the base header file and copy the code snippet that deletes the copy and move operations. Then, let's paste it into the logger class. Even though this class doesn't handle dynamic memory or other complex resources, it is better to explicitly disable copy and move operations. This prevents shallow copying and helps maintaining encapsulation. For example, in case a function like getLogger from the base class returns a reference to the logger. By deleting the copy move operations, it will never be possible to accidentally replace the logger instance with a new one. Also, remember to add the distractor to follow the rule of 5. Finally, let's go to the game C++ file and improve the log message in the game distractor. Let's change it to game is shutting down. This message is clearer and more descriptive. After this brief refactoring, let's finally start with the creation of our device context. Let's create the device context class. As usual, let's move the header and C++ files inside the graphics folder within the source branch. Remember, for now, we don't want to expose our low-level graphics resources to the users of our DX3D engine. We are now ready to implement our device context. As always, let's wrap the device context class inside the DX3D namespace. With that done, let's make the class final and extend it from the graphics resource class. Of course, we need to include the required header files. Now we are going to take care of the constructor. As usual, let's start by adding a parameter that is a constant reference to a graphics resource descriptor object. Since we don't plan to add more parameters, we should mark it as explicit to prevent unintended implicit conversions. Alright, let's implement the constructor. Here, we should replace the include directive to follow the same style used in other files. At this point, let's call the graphics resource constructor in the initializer list and pass in the descriptor. We are now ready to call a D3D11 API function from the D3D11 device. That is the create deferred context function. As usual, we need to pass some parameters. The first one is context flags. This is a reserved parameter that doesn't affect the creation of the deferred context, so we can safely pass 0. The second parameter is an output parameter that we receive the D3D11 device context instance. To handle this, let's go to the device context header file and add a com pointer to the D3D11 device context. Let's call it context. Now let's return to the device context C++ file and pass this member as the output argument to retrieve the context. As always, let's check the result of the function, log a message, and throw an exception if the function fails using the dx3d graphics log throw on fail macro. Let's make sure to write a proper log message. So far so good. With that completed, let's move to the graphics device header file and start implementing the create device context method. As usual, let's go to the core header file and add a forward declaration for the device context class. Let's also add a type alias named device context pointer using the shared pointer. Now we can return to the graphics device header file and use the device context pointer as the return type for our create device context method. We are ready to implement it. Let's use the makeshared function. Let's pass the class type as the template parameter and call getGraphicsResourceDescriptor function to pass the resource descriptor. Let's also remember to include the device context header file. What's next? We need to finally create and use our deferred device context. Let's go to the graphics engine C++ file. Here we can define a reference to the graphics device. Let's call it device. At this point, we can call the create device context method. No parameters are required, so that's it for the call. Now that we have created the deferred device context, we should store a pointer to it. So let's go to the graphics engine header file and add a device context pointer named device context. Always remember to initialize the member using curly braces, which is the modern and preferred approach for variable initialization in C++. In the end, we can use it inside the graphics engine constructor. What we need to do now is create a very important method in our graphics engine class, called render. As the name suggests, this function is responsible for rendering the final frame to be presented on the screen, more specifically, in our case, inside the application window. Alright, let's implement it. First, we need to get a reference to the device context. Let's include the appropriate header file so we can use the device context class. As we saw in the introduction, a deferred context records a list of commands to be passed and executed by the GPU for various purposes, including graphics rendering. The first command we should record is the one to clear the content of the buffer, where 2D or 3D graphics objects will be rendered. As we discussed in the last tutorial, once we finish rendering objects to the buffer, more precisely the back buffer, we need to call present to perform the swap between the back and front buffers. This allows the GPU or DWM in case of windowing mode to display the frame on the screen. That said, we can now proceed to the device context class and add a method called clear and set back buffer. As the name suggests, this method should record a rendering command that clears the contents of the back buffer with a specific color and binds it to the graphics pipeline, so that all subsequent draw calls are directed to this buffer. We will dive deeper into the graphics pipeline topic in the next episode. Of course, the back buffer is retrieved from the swap chain, so as the first parameter, we should pass a constant reference to the swap chain. As the second parameter, we should pass a color value, the color that we will use to clear our back buffer. However, we currently don't have a class to represent this color. So let's go to the math folder and create a new header file named vec4. Vec4 stands for a four-dimensional vector composed of four attributes that usually represent space coordinates. But in this case, we will use it to represent a color made of four color channels. Let's begin by adding the DX3D namespace and defining the vec4 class. Here we can use the rule of zero, where we only implement the constructor. In particular, let's use the default constructor, as we don't need any special operations at this stage. Then, let's create the public attributes of the vec4 class. We will keep these attributes public to allow easy access without the overhead or indirection of getter and setter methods. Let's start by adding the first float attribute named x. We will include the core header file to get the F32 type definition. Finally, let's add the remaining three attributes, y, z, and w. At this point, we can also add an overloaded constructor. Specifically, we want a constructor that allows us to create a vec4 by passing all four components directly. Alright, with that complete, let's go back to the device context and add the second parameter of the clear and set back buffer method, that is, a constant reference to a vec4. We are ready to implement our method. The first command we will record is the clear render target view. We can do that by calling the corresponding method from the deferred device context. As the name suggests, this function allows to clear the content of a particular object called render target view. We need this function to effectively clear and fill our back buffer with a specific color. Let's see how to do it. This function requires two parameters. The first one is a render target view, or RTV, which is an object that represents a view into the so-called render target. Before proceeding further, let's take a moment to organize things and break down these concepts clearly. In Direct3D 11, rendering happens by drawing into a texture, which is simply a block of memory used to store pixel data. One special kind of texture is the back buffer, which is created by the swap chain and serves as the target for rendering each frame before it's displayed on the screen. To render into any texture, including the back buffer, you need to treat it as a render target. However, Direct3D requires an extra step. To treat a texture as a render target, you must create a render target view. The RTV acts as a wrapper around the texture, describing how the GPU should interpret it when rendering. So the process goes like this. The GPU uses the RTV to bind the back buffer, that is a texture, as the active render target, performs the rendering, and then the back buffer is presented to the screen. To sum up, we need to create a render target view from the back buffer, which is nothing more than a texture created by the swap chain, so that we can render into it. So let's go to the swap chain header file and add a private method called reload buffers. Now let's implement it. This method should retrieve the back buffer and create a render target view from it. First, let's retrieve the back buffer by calling the getBuffer method from the swap chain interface. The first required parameter is the buffer index. Here we must always use 0 since it's the only valid index to get the back buffer in Direct3D 11. Then we need to pass a pointer where the buffer would be stored. As usual, with these API calls, let's use the IID macro to retrieve the current interface pointer based on its ID. Here we must create a COM pointer to D3D11 texture 2D called buffer and pass it to the macro. As usual, let's use the log throw on fail macro to check the result and throw an exception if the call fails. With the back buffer retrieved, we now need to create the render target view from the D3D device. The first parameter is the texture resource we want to create the view from, so we pass our back buffer. The second parameter is the render target view descriptor. We can safely pass null pointer here to create a default view. The final parameter is the pointer to receive the RTV instance. So let's go to the swap chain header file and add a COM pointer member for the render target view. Pass it to the function, and again, finalize the call with the log throw on fail macro. So far so good. Now that we have the view, we can go back to the device context and retrieve it. To do this, we need to include the swap chain header file. However, since the attributes are private, we can't access them directly. Also, we want to avoid exposing Direct3D 11 interfaces in the public methods of our engine classes. To handle this, we can take advantage of a useful feature in the C++ language, the friend class. In C++, a friend class is allowed to access the private and protected members of another class. This allows us to bypass encapsulation in a controlled way, often used when two classes are tightly coupled and need to collaborate at a low level. In our case, device context and swap chain are tightly coupled, since the context needs to access internal swap chain resources to efficiently perform rendering operations. Keep in mind that using friend is generally discouraged, especially in high level or public facing API code, because it breaks encapsulation. Only use it in specific justified cases like this, where two core internal components of the engine must interact directly. So, as a general rule, avoid friend class and only use it when absolutely necessary. Alright, now let's go back to the device context and retrieve the RTV. Then we need to pass an array of four float values, representing the color channels red, green, blue, and alpha. Let's create a float array using the x, y, z, and w attributes from the vec4 parameter. The values should be in the range 0, 1. Let's pass the array to the function and finalize the call. Last but not least, let's call omSetRenderTargets, which allows us to bind the buffer we want to render graphics into. The first parameter is the number of render target views. We are setting only one view, our back buffer. Then we need to pass an array of pointers to the views. Let's create a row pointer called RTV and let's use the get function from the com pointer we've written previously. Let's pass this pointer to both the clear render target view and the onSetRenderTargets functions. To simulate an array here, we can take the address of the pointer using the AND operator. This gives us a pointer to an array of RTV pointers. Finally, for now, pass null as the depth-stencil view. We will cover depth-stencil view later in the series. Alright, what we need to do now is go to the graphics engine header file and finalize the render method by adding a swap chain reference parameter. We are using a non-null reference here because the function should not accept a null swap chain. We are also defining this parameter to allow the graphics engine to render to a specific backbuffer of a swap chain. Let's copy and paste the parameter in the corresponding C++ file. Finally, let's record the rendering command that clears the content of the backbuffer and binds it so we can render graphics elements onto it. Let's clear the backbuffer with a red color, setting the red channel to 1, green and blue channels to 0, and the alpha channel to 1. This tells Direct3D that the color is fully opaque and doesn't have transparency. Alright, let's move to the next step. We now need to allow the GPU to execute the list of commands recorded by the device context in order to finally render something to the back buffer. To do this, let's go to the graphics device header file and add a new method called executeCommandList. Let's define it to take a non-null reference to a device context. Now let's implement this method. Here, we will use the immediate device context we retrieved during the Direct3D11 initialization. Let's call the executeCommandList method on it. Unlike the deferred context, the immediate device context doesn't record commands, it sends them directly to the GPU as they are issued. That's why it's called immediate. The first parameter we need to pass is a row pointer to the command list. To get this, we must retrieve the recorded command list from the passed in deferred device context. However, we currently don't have access to its private attributes. So let's go to the device context header file and let's make graphics device a friend class of device context class to allow graphics device to access the internal members of device context. Now let's return to the graphics device C++ file and access the internal context attribute. We can now extract the command list recorded by the device context using the finish command list function. This function takes two parameters. The first is a Boolean flag that specifies whether to restore the previous graphics pipeline state. For efficiency and optimization, we should always pass false here, unless there is a specific reason to restore the state. We will explore graphics pipeline state in the next episode. The second parameter is an output parameter for which we can retrieve the command list. Let's create a pointer to hold the command list and call it list. Then pass it to finish command list function. As always, use the log throw on fail macro to check the result and handle any errors. With the command list now available, we can pass it to the execute command list function. This function asks whether we want to restore the context state. The restore context state parameter decides whether to restore all context states, including the graphics pipeline state, to their values before the command list was executed. Always for efficiency and optimization, let's pass false. So far so good, now let's go back to the graphics engine C++ file. Inside the render method, let's get a reference to the graphics device, and then call the execute command list method. Of course, we will pass the device context from which we extract the command list to be executed by the GPU. We are now ready to present our back buffer with its rendered content on the screen, or more accurately on the window. To do this, let's go to the swap chain header file and add the present method. Here we can define a Boolean parameter called vsync. vsync, short for vertical synchronization, is a technology used in graphics rendering to synchronize the frame rate of a game or application with the refresh rate of a monitor. The goal of vsync is to eliminate screen tearing and ensure that frames are displayed smoothly. Let's set it to false by default. At this point, let's proceed with the implementation of this method. All we need to do is call the present method of the DXGI swap chain interface. The first parameter is the synchronization interval, which controls how the GPU synchronizes frame presentation with the monitor's vertical refresh rate. If we set it to 0, we have no vsync, and the frame will be presented immediately. However, this may cause screen tearing. If we set it to 1, we wait for one vertical blank, which typically limits the frame rate to 60 fps on a 60 Hz monitor. This prevents tearing but may introduce some input lag. If we set it to 2, we wait for two vertical blanks, which limits the frame rate to 30 fps on a 60 Hz monitor, though it is rarely used. The same principle applies as we increase the value, with each higher number waiting for more vertical blanks, and further limiting the frame rate. Let's pass the vsync parameter here. If it is false, we pass 0, which means no vsync will be applied. Otherwise, if it is true, we pass 1, meaning we will wait for one vertical blank and so syncing with the monitor's refresh rate. The second parameter is the presentation flag. Let's pass 0, which means no special presentation behavior is requested. As always, let's check the result with the log from failed macro. Now let's return to the graphics engine C++ file, and inside the render method, let's finally call the present method after execute command list. And with that, we have completed the rendering process. What we need to do now is go to the game header file and add a private method called onInternalUpdate. This method should act as a callback where we can place all the code that needs to be executed each frame. Usually, when implementing the method using Visual Studio, the generated code might end up inside the Win32 game C++ file. However, since this method should not contain platform-specific logic, it should not be placed in a platform-specific file. So let's cut and paste the implementation into the game C++ file instead. Now we can call onInternalUpdate from within the Win32 game C++ file, replacing the sleep function call. Previously, we used sleep to prevent excessive CPU usage because there was no rendering involved. But now that rendering is implemented, this is no longer necessary. Next, let's go back to the game C++ file, and in the onInternalUpdate method, let's call the render method of the graphics engine class. At this point, we need to pass the swap chain as parameter. As we saw in the previous episode, the swap chain is created inside the display class. So let's go to the display header file and add a getSwapChain method that returns a non-null reference to the swap chain. Let's also mark this method with the noExcept keyword. Adding const here is not necessary since we are not returning a constant reference. We will cover this topic in more detail shortly. Now we can implement the method. Remember to prefix swapchain with the dx3d namespace. We could also use using namespace dx3d, but as previously mentioned, we should use that only when strictly necessary. Let's dereference the swapchain shared pointer in the return statement. With that done, we can go back to the game C++ and pass the swap chain by calling the getSwapChain method of the display class. Be careful here. We also need to go to the swapchain C++ file and call the reloadBuffers method inside the constructor. This ensures that we have a render target view of the back buffer ready to be used by the device context. Let's finally debug our program. And here we go. The back buffer is now displayed inside our window. As expected, the back buffer has been filled with a red color. At this point, let's go to the graphics engine C++, and if we also set the green channel to 1 in addition to the red one, we should get a yellow color. Let's see if it works. It works. Let's go back to using red color. Great, we have finished this tutorial, but there is one last topic to cover. If we go to the graphics engine header file, we will find a method called getGraphicsDevice that we have marked as const. Since we are returning a non-const reference to an internal attribute of the class, we are essentially allowing users to modify that internal state. We should mark this particular method as const if we return a const reference to the attribute. Since that's not the case here, let's remove the const qualifier from the method. Let's do the same for the base class. Remove const from the getLogger method. Then go to the logger header file and make the log method non-const as well. Despite the fact that the log method could technically be made const since the internal state of the logger is not changed, we use the clog, which is a global output stream that can change its state during the logging process. While the logger itself doesn't change internally, it does affect a globally accessible stream. Therefore, it's preferable to make the log method non-const. Lastly, let's go to the display class and make the getSwapChain method non-const. To wrap things up, let's remove the empty graphics folder from the public API located in the include directory. That's all for now, folks. Today we learned how to create and use the device context class. We saw how to record rendering commands into a command list using the deferred context. In particular, we learned how to clear and fill the back buffer with a red color. We also explored how to extract a command list from the deferred context and send it to the GPU for the execution by means of the immediate device context. In the end, we swapped our back buffer with the front buffer to finally present it on the screen. In the next episode, we will dive into the graphics pipeline, the foundation that will lead us to finally render a triangle on the screen. I hope you enjoyed this video. See you soon. Thanks for watching.